So we spent a little while talking about angular momentum so far, sort of how to calculate angular momentum, kind of what the direction, what the units of angular momentum are, and this sort of idea that you can think about angular momentum as being made up of both a component that's due to a particle abstraction and a component that's due to the sort of blowing that particle out into a rigid body. We're now going to move on to asking the question, how does angular momentum change? And to do that, we're going to continue with this linear angular analogy, right? In linear motion, the thing that changes momentum is force, right? Force is a flow of linear momentum. And in the angular case, torque, which is denoted with a tau, Greek letter tau, is the thing that causes the change in angular momentum. Torque is a flow of angular momentum, and torque is obtained by taking the cross product of the position that the torque is applied with the force. Okay? And I just want you to sort of kind of note this sort of interesting thing that's going on here with this cross product with the position vector, right? Just like angular momentum is a cross product of the position vector with the linear momentum, torque is a cross product of the position that the force is applied with the actual force. If we think about units of torque for a second, right? It's going to be Newton meters. So same units as work, although of course torque is not actually telling you anything about work. It's telling you what the inclination is of a given interaction to cause the angular momentum to change. So you can think about torque as the thing that causes angular momentum to change, or sort of more colloquially, the sort of thing that causes rotation. Okay. So one sort of quick example to kind of highlight a couple of ideas about that. You'll note, first of all, that torque depends on what your position vector is. So it seems like origin is going to matter for torque, and it also depends on how much force you're talking about. So let's do a sort of simple example of that. I've got a nut here, and I've got a wrench, which I'm using to try to turn the nut. Obviously, if I wanted to tighten this, I would want to apply a force to the wrench, and you sort of know from experience probably that if you try to apply the force here, it's not going to tighten nearly as effectively as if you apply it here. This is why when you're changing the tire on a car, you need a relatively long tire iron because it gives you what's called a longer moment arm. Intuitively, you also know that if you were to apply a force like this to the wrench, it wouldn't tighten the nut very effectively, right? You actually need to apply a force in this direction in order to tighten the nut. Applying a force in this direction is not going to tighten it at all, and applying a force in this direction will actually cause it to loosen. And I bring that up because you can think about this from a torque perspective, right? Torque tells you what the tendency is to cause rotation, but from a mathematical perspective, torque is a cross product of the position that you're applying the force with the force. So let's think about what the torques are that each of these possible forces would cause. So I'm going to say that's force A, this is force B, this is force C, and let's say this is force D, right? So force A, well, R is going to be, if I'm calculating the torque about this bolt, right, the position that that's going to be applied at is R1. So I'm going to say that's L in the I hat direction, right? This is L long. And the force is whatever the value of the force is in the negative J hat direction, right? So my torque in this case is going to be L times F I hat cross negative J hat, so minus L F K hat. So for the case 1, for case A, the torque is into the page, and it has a magnitude of L times F, right? F sub B, R is still L times I hat, but force B is the magnitude of the force times minus I hat. I hat cross minus I hat is 0, so force B doesn't tend to cause any rotation. It's got 0 torque associated with it, right? Force C is going to give me a torque of plus L times F times K hat, right? it wants to cause a rotation that's in the positive direction, so the torque is coming out of the page, right? And finally, force D, even if it's just as big a force, if this is a much smaller distance, let's call it D, force D is going to give me a torque of minus D times F times K hat, which is going to be less than what the, and this is force A, each of these yields a torque. This will be less than the torque due to force A. And I apologize, I wrote F's here and I meant to write torques here. So each of these forces, even though they're the same force, causes a different torque, right? And the value of the torque both depends on where the force is applied, right? Depends on this R, and also depends on what the direction of the force is that it's applied in because of this cross product.